Hello everyone, how are you all? So we will start with this webinar. So I am Harsh Shah from Renewsys India Private Limited based at Mumbai, and I have my colleague named Mr. Sandeep who will be presenting the technical part of this PPT. So I will take you all to the small introduction about Renewsys. So Renewsys is basically the first integrated manufacturer of the components and PV models. So we manufacture EVA, backsheet, solar PV cells, and solar PV modules. Sandeep, next slide. We will start. So Renewsys basically is a part of NP Group. NP Group is in the industry since 58 years now. So we have around 58 to 60 years of the manufacturing experience. We have 3,000 plus employees working in our group with the group turnover of $350 million plus. Sandeep, next. So NP Group is a group basically having many industries. So out of all these industries, apart from solar PV modules and its key components, we also manufacture cement roofing sheets, soaps, chemicals, beauty care products, and many more things. So we have few industries in Nigeria, and our renewable arm, which is Renewsys, is based in India. So we have factory at Hyderabad for solar PV modules and solar PV cells, and we have factory at Bangalore to manufacture EVA and POE and also the backsheet. Sandeep, next. Okay, so this is the global presence where we have offices globally in Dubai, Nigeria. We have offices in Singapore, India. We have representatives around the globe: Brazil, Mexico, USA, Europe, at Czech Republic. We have warehouses at different places, and manufacturing is in India. Sandeep, next. So this is a Renewsys journey. So Renewsys started in 2011 with only EVA. Later, we started with the backsheet, and gradually we increased our capacity of EVA and backsheet. Then in 2015, we acquired Solar Semiconductor, which was the company who was manufacturing solar cell primarily and modules for USA. We have acquired that, and we developed that factory. We did expansion of the PV modules and the solar cell line. So at present, our solar cell line capacity is 130 megawatt, and our manufacturing capacity of solar PV modules is 750 megawatt. Sandeep, next. Okay, so this is Product Excellence Center. So in India, we have factory at Hyderabad, as I mentioned. So we have 7 climatic chambers only in India. So at Hyderabad factory, where we do our reliability testing. We also do 3 times IEC testing in-house, so that we rest assured about the warranty what we are offering. So our field performance remains intact because all the necessary testings are done in-house. Also, Renewsys Hyderabad laboratory is Intertex Singapore. It is Intertex Satellite Laboratory, basically approved by Intertex Singapore. So we have facility to do in-house testing and in-house certification. Sandeep, next. Okay, so from this slide, Mr. Sandeep will take over and he will explain to us on the concept of full cell and half cut cell. Sandeep, please take it ahead.
Thanks, sir. Thanks a lot.
Thank you.
Good morning, everyone. This is Sandeep. I look after product development and reliability lab at Renesas PV module manufacturing facility. So, the current technical topics what we are going to discuss today in this webinar are of two things basically. One, full cell versus half cut cell. Why we do half cut cell? Why half cut cell is having an advantage over full cell? That is the first part. And the second part is towards the reliability of the solar modules. That is how important it is to select the key components when we make a solar module and its impact on the lifetime, because solar modules are generally warranted or guaranteed for 25 years. So coming to the current topic of full cell and half cut cell, uh, uh, before understanding this actually, we would like to know why industry, the PV industry is looking for this. Okay, in the PV industry, the innovation is majorly considering the two aspects, that is bringing down the cost of installations and at the same time lowering the LCOE, that is levelized cost of energy. So these are the two key components which are driving the PV industry in innovation. So a glimpse of what it used to be and what it is now, if you see, or what it is going to be in future, uh, like the price for installation of a kilowatt system is currently in 2018 is roughly around 1210 USD per kilowatt peak, which is expected to drop down to 165 to 481 USD per kilowatt by 2050. If not earlier, latest by 2050. And similarly, the LCOEs, the levelized cost of energies, are going to drop so low that of the available energy resources, comparing to the current normal non-renewable energies and including the renewable energies, even if you including the nuclear, solar is going to drop down so low, and it would be the cheapest source of energy production. And yeah, this is the graphs here indicate the installation costs across the different regions. What were they when in 2010, and how did it come down by 2010? Sorry, 2018. So if you see the cost of installation was around 4,600 USD roughly per kilowatt peak in 2010, which has come down to 1210 USD by 2018. So this is a steep decrease in 8 years at a percentage of 74%. So this is very much high. So similarly, if you look into the installation costs across regions, how it had dropped. If you see in Europe, it has dropped by around 72%, in India by around 84%. And if you come to United States, which is holding strong, but still the percentage is very high, which is around 66%. So the price from 2010 to 2018, it has decreased by 66%, which is expected to drop down further, making solar as the cheapest and viable option across all the energy sources what we have. Similarly, these graphs talk about the LCOEs and predicted forecast, how it is going to be in future. So the global LCOE costs also have dropped by around 77%. Now, if you see LCOE costs of solar energy, earlier they were high, but now they are comparable to fossil fuels. In some of the locations and some of the regions in the recent allocated tenders, solar power, the LCOE for solar power is much below the fossil fuels. One of the few reasons, means like few of the reasons for this to be there is the competitive procurement. The number of people who are producing solar have increased. The competition has increased, so giving a buyer an option of bargaining the price. And similarly, the bankability for the solar projects have increased, and because of which the financing costs also have become low. All put together is resulting in the lower LCOE cost for the solar industry. So currently, if you basically solar cell is the key component of any solar PV modules. So the industry trend or industry where it is working or where it is looking for in the cells, in the solar cell part, actually, if you see, Right now, PERC, passive emitter rare contact technology, has become an industry standard. Mono is going to dominate. No poly. Poly is going to diminish. Mono is in term, and everyone are going to offer PERC technology only. But this has become industry standard. But the other two technologies which are being considered at this point of time and which are going to pick up very fast are heterojunction, that is multi junction. One of the key customers who are using this is REC Group. Key manufacturers using this is REC Group. And second, other technology which is picking up very fast is TOPCon, which is tunneling oxide passivated contact, where we have an oxide layer on the surface of on the backside to further increase the passivation, thereby increasing the efficiencies of the solar cells and the power production capability of the solar cells. So now this is also picking up very fast in the industry. Most of the Chinese manufacturers, tier 1 manufacturers, are going for this. Trina is one good example for this. So these are the industry developments from solar cell point of view. Then if you look into the solar module point of view, earlier it used to be believed that since in a solar module, since solar cell is the current generator, research has to happen or developments have to happen from the solar cell point of view, and then module is made. But now the perception of the module manufacturers have changed. They are looking for innovative technologies with which they could also contribute in increasing the power of a solar module and increasing the efficiency of the solar modules. So for few of the key concepts, what they are considering is reduction of the resistive losses, improving the reliability of the solar module, thereby increasing the lifetime of the solar module, decreasing the degradation rates of the solar module. Then bifacial technologies, wherein which we can use the rear side, whatever we are getting from the rear side also to be absorbed, and the reduction of the cell spacings, thereby decreasing the size of the whole solar module, increasing the efficiencies. These are few of the things which are being currently worked. So some of them are multi-bus bar, which is not standardized, but it is up to like 9 bus bars, 10 bus bars, 11 bus bars. It goes up to 15 bus bars. Starting from 9 to 15 bus bars, whenever we use these multi-bus bars, actually, the copper which is used to connect these solar cells in series would be a round wire, thereby decreasing the reflective losses and increasing the power. Glass-to-glass modules offer more rigidity, offer more mechanical strength, less degradations with the harsh environmental conditions what we have. Bifacial modules, power from both sides. Half-cut cells, which we are going to discuss technically in this presentation, are going to increase your performance under shading, under high temperature operating conditions. Then comes shingles. Shingles is other technology which is being considered, but it might take time for it to take it up. But like the most important thing, which is going to be the core scope for product development in the module, would be the larger wafer formats, because most till now, like till 2019 mid or so, industry is almost standard at 156 or 157 mm size. But now if you look into it, the mono solar cells have increased to 158.75, which is hardly going to stay about for 6 months to 1 year. From there on, it is going to go to 166, very rapidly to 182 or 210. So when we are using this, when we are using larger wafer formats, the size of the module is going to increase. Once the size of the module is going to increase, the weight of the module is going to increase, there in which we are going to have an impact towards the BOS components. So in order to avoid this, the equipment manufacturers have started developing technologies like paving and tiling, wherein which the gap between the solar cells is reduced. So these are the few product development or new concepts which module manufacturers are working on. So now coming to full cell and half cut cell design, why is it advantageous, or what are the basic differences? What is the difference in terms of manufacturing, in terms of installations, what in terms of performance and all those we are going to see in this. So now, why we should go for cut cell technology? Okay, the basic simple concept behind this from the manufacturer's point of view is simple. So if you take power loss, because each an individual solar cells, depending upon the form factor, we are going to go either 60 cells or 72 cells. They are connected in series, and we are adding a resistance, that is a copper ribbon, which is used to connect the solar cells. So the net power loss is the current squared times the resistance what we are adding. So if I assume I to be the current of a full solar cell and R is the resistance which I've added, the net loss, or the CTM, which is basically cell to module loss, is I square R. Now, if I cut the cell into half, one of the key thing in solar modules or solar cells is the amount of current what we are going to generate out of the solar cell is directly proportional to the area of the solar cell. So since we have cut the solar cell into half, its area has become half. So indirectly, directly, the current that solar cell, half cut solar cell is going to produce has become half. And the CTM loss, that is the cell to module loss of a half solar cell, would be I by 2 whole squared by R, which is ultimately decreasing the net amount of resistive loss or the power loss by 1/4. So this is one of the key reason why industry is looking for cut cell technologies. Then we can further say why not 1/3 cut or why not 1/4 cut. But if we do, the amount of net impact in 1/3 or 1/4 is going to be nominal, considering the current size of solar cells. So one half of the solar cell is good enough, and we could attain the maximum gain what we can attain in terms of CTM.
Sandeep, sorry to interrupt.
Yeah.
Dear all the guests, I understand you all have the questions to ask. I can see people are raising their hands. So it will be really helpful if you all can keep the questions for the end. We will have Q&A sessions where Sandeep will be answering to all the questions. Thank you, everyone. Sandeep, go ahead.
Yeah, thanks. Okay. Now, from full cells to half cells, in detail, if you wanted to understand, actually, the pictures on the right indicate how is the current flowing in a general solar module. So the area of a solar cell, when we are considering half cut solar cell, is cut into half, resulting in the reduction of the current, which I've already said, through the bus bar. That is, now suppose if just for an example, if we take a solar cell producing 10 amps and it is having 5 bus bars, so each bus bar is going to carry 2 amps. So now if we cut that into half, each bus bar is going to carry 1 amp. So that is how you are going to reduce the current through the bus bar of a solar cell. This decrease in the electrical resistance would increase the efficiency of the solar module, overall efficiency of the solar module, because in the same given area, you are going to produce slightly higher power, which is roughly around 1.5 to 3%. And this reduction in series resistance would increase the fill factor of the solar module when you compare fill factor of a half cut solar module when you compare it with a full cell solar module. So in terms of design, to simplify it, we can consider a half cut solar module to be 2 modules which are connected in parallel and are joined in between. So the upper half is a one module by itself, where all the solar cells are connected in series, and the lower half is one more module where all the solar cells are connected in series. Suppose if you take a 60 cells, the upper half is going to have 60 half cut solar cells, and similarly the lower half is going to have 60 solar cells which are connected in series. And both these upper half and the lower half, that is the upper module and the lower module, are in turn connected in parallel, thereby giving the same voltage and current ratings, but decreasing the net power loss what we have. That is improving the CTM, improving the efficiencies, and improving the fill factors. In terms of module manufacturing, what means in terms of PV module manufacturing, that is for the half cut, how is it different from the full cell module manufacturing? So the first thing what we have to consider is there is an additional step in half-cut solar module manufacturing. That is, when we get the cells, these need to be cut into half. This can be cut into half either by using laser or by mechanically, but mostly it is using laser, which is what it is used in the industry, across the industry. So once laser gives a scribe on the solar cell, it is cleaved to form two half-cut pieces which are uniform in nature. Now, from quality point of view, there are few disadvantages, potential disadvantages or few disadvantages which industry has coped up with and developed the technologies or the equipments whichever are required to cope up with this. But typically, one thing what we have to see is since if you take a half-cut solar module, it is practically two modules which are connected in parallel. So the number of solder joints what we have will become almost double. That is the first point. Then coming to the second point, cutting the solar cells using laser will slightly cause a inherent damage to the surface of the solar cells and to the depth of the solar cells where how much ever it cuts. But now these bad contacts, inherent defects can be prevented during manufacturing with proper quality control, that is having proper detection systems wherever it is required across the line. But generally, half-cut solar modules are expensive. That is compared to a normal full cell module. The precise reason is that we have an additional manufacturing step which would increase the cost of a half-cut solar cell module when compared to a full cell solar module. And if you look into the advantages of the half-cut solar cell module over a full cell module, predominantly when we install solar modules on rooftops or on open areas which are not large like a utility scale, there is a major chance we get shade of the adjacent building, shade of a tree, shade of the pole of a current pole or so. So when we have this in a full solar cell module, if one cell is shaded, we are going to lose about 1/3 of the power. And if we are going to shade the bottom most of the solar module, then the power produced by this module would be zero. But now coming to a half-cut solar module, even if you completely shade the bottom most, still the module is going to produce 50%, which is an obvious benefit for the end installer. So that is the main advantage of using a half-cut solar cell module from installation point of view. And the second most important point to be considered are the temperature coefficients. Since the solar cell is cut into half, the current it is going to carry is half. The net amount of temperature it is going to release is going to be less. So the temperature coefficients for these solar modules which are using half-cut are going to be better when compared to a full cell module. This graph typically depicts what would be the power we are going to lose at different temperatures. Here it is consistent. So suppose if we take 25%, both full cell and 25 degrees centigrade, both a full cell and half-cut cell are producing 100%. But as and where when the temperature is going to increase to say at max we have shown here 75, you could see that the amount of power lost in a full cell module is higher when compared to that of a half-cut cell module. So now we'll come into installation schemes for half-cut solar cell modules. That is a portrait, landscape, and all this stuff. So portrait installations of a solar half-cut solar. Typically, half-cut solar cell modules are going to have the junction box in the middle of the module rather than on one side of the solar module. So while we are going to install for half-cut cell modules, cables and connectors, the approach with which we wanted to do this need to be slightly modified. For half-cut cell solar modules, during installation, particularly in portrait, it's not going to be a major issue. Whether we are having the rafters or purlins which are going into the near the mounting holes or at the edges of the solar modules using clamps. So in fact, if you see, actually, when you are using the mounting holes provided in the solar modules, half-cut solar modules are going to have an advantage where the cables are free to access when compared to a full cell module, where generally the junction box is towards one side of a solar module. Now, coming to landscape installation, this is the place where these half-cut solar modules are going to have an issue with. So we need to, whenever it is desired to be installed in landscape, upfront information to the module manufacturers to be given so that they can provide the appropriate cable length required during installation process. So when we are in as you've seen a half-cut solar module, if you see on the image towards the left on the top, so the length of the cable is not enough to connect the adjacent module. So upfront, if an information provided upfront would be helpful for the installers and the module manufacturers to provide appropriate modules, whereas that is not the case when you look into full cell modules. So now final comparison between a full cell module and a half-cut cell solar module. So the voltage rating of the full cell module are normal, but when you compare the same means using the same efficiency of solar cells which are cut into half and made a module, the voltage rating would be slightly higher. Temperature coefficients, which we have discussed, which is the major advantage of half cell modules. Full cell are going to have higher temperature coefficients, and half cell modules are going to have a lower temperature coefficients. And fill factors, which are basically dependent on the resistance what we are going to add, obviously say that full cell modules are going to have a lower fill factors compared to that of a half-cut cell module. Module construction or module manufacturing, full cell module, it is very easy. Equipments are there, everything is easy. Whereas in half-cut solar modules, since solar cells are already delicate, which are very thin, around 200 to 180 microns, by cutting them, it is going to be slightly difficult. Module efficiencies typically for a full cell module are going to be between 16 to 19%, whereas for a half-cut solar modules, they are going to go up to 21%, starting from 17%. In terms of installation, sizing, compatibility with inverters, it's going to remain same. There is no much difference. Module mounting systems, industry standards means since full cell modules are there since a long time, mounting structure wise there is no issue. But when you come to half-cut cell solar modules, prior planning is required, considering if you wanted to use a leapfrog or landscape installations. But it should not be a problem when we wanted to use it in a portrait. So in terms of application types, full cell modules can be used as a residential, commercial, and utility scale. But considering the advantages what half-cut solar cell module is going to offer, it is more useful for commercial and residential applications. Cost, as we have discussed earlier also, full cell module are on the lower side compared to that of a half-cut cell module. Technology, how long it has been we are having this model. Full cells are over modules made using full size solar cells are more than 25 years are being in the field. But when you come to half-cut cell solar modules, typically it is around 10 years, if not early. It started in 2010, 2011 time. So it is typically 10 years life what we have seen for half-cut solar cell modules. Availability, now I will say it is widely available in both the cases, both full cell modules and half cell modules. But considering where industry is going to go in terms of the product developments, this might change in near future. Maybe in 1.5 years, full cell modules might be rare, whereas half-cut cell modules are going to take over. Others, old means full cell modules are very old and proven, and it is a new technology. If you take half-cut cells, what in terms of warranty, both models offer the same thing. So then now let us go to the second important topic, which is the reliability of a solar module. Typically, why is it important is because unlike any other product, a solar module is warranted for 25 years. So whatever investments we are going to make, we are making with a warranty of 25 years. So it's very necessary, very important for anyone to look into the reliability of the product, whether it's going to sustain for 25 years or not, how a module manufacturer should take care in order to have this, is what we are going to discuss over here. So this graph over here typically shows the failure schemes at different over the 25 years at different stages of its life. What are the typical failures which were observed in the industry till now across last few 15 to 20 years. So the starting infant failures, which would range from 0 to 5 years typically, are LID, which is around 0.25%, but it is inherent nature of these solar cells, so that cannot be avoided. But coming to the other failures, which need to be considered here, are contact failures in the junction box, that is improper connection schemes inside the junction box. String interconnect failures. String interconnect failures are the ones when we connect these strings in series, if they are not connected properly, they are going to create arcing. There might be a backsheet burning and so on. So then the other thing is the glass breakage. Typically, solar modules are larger in size, typically around 2 meters or beyond 2 meters, and a tempered glass is being used. So if proper glass is not being used, it is going to break, and it is going to be a safety hazard. Then the other thing is a loose frame. If the frames, because the modules are going to install in the field where it is going to see the dust, gust, wind speeds, and all those stuff. So if the frames are not proper, they are going to mechanically damage the module, and we have seen worse conditions where module fly off from the structures as well. Now coming to the middle life failures. Nowadays, all the glasses which are used in solar industry are AR coated. If there is a slight amount of degradation in any of the AR glasses, but if the AR coating is not selected in such a way it should last for 25 years, it is going to cause a huge problem. Now, coming to the other middle life failures, PID, which is spelled as potential induced degradation, is one of the key failures which we have seen in the recent past. The reason for this is the increased system voltages. That is, like industry started with 600 volt systems, it has moved to 1000 volts. Now it is going to 1500 volts. So the higher the voltage, the more effect on the solar modules which are at the fag end, and the more chance that these modules are going to fail if proper care has not been taken. Then comes diode failures. Basically, these diodes are the diodes which are there in the junction boxes, which are called as bypass diodes. These are generally Schottky diodes. So when we have shade, these diodes are there to protect the module from the hotspot effect. That is, not to increase the temperature of the module so high that it is going to damage the backsheet TV of the solar module. But if proper care is not being taken while installing these junction box or manufacturing of modules, these diodes are going to fail. And then cell interconnect breakage, which is again the same thing which we have discussed earlier. Now, apart from that, the fag end failures are going to be EVA discoloration, which are typically around 10 years or beyond 10 years, delamination, cracking of solar cells, corrosion of cells and interconnects. These are the wear out life. These are okay. These are going to happen because of the harsh environment these modules are going to undergo. Now, this is a typical field data across few sites on an audit conducted or survey conducted by a company called PV Diagnostics in India. Okay. They have done it across 4 sites, typically of 10 megawatt or 28 megawatt or even larger. And we can see when these modules have been commissioned. And so all of the modules used in this are made using multicrystalline solar cells, which was the industry standard then. Now it is going to change to mono. So if you see, the average degradation of the modules is typically on the very higher side, because the lowest, if you see, is around 12% and the highest is around 18%, and it has not been, it's been like 4 or 5 years these modules have been installed in the field. So So what it says from this graph is it is very much important. And if you see the older the models, in fact, older models are performing better when compared to the new models what we are now. The typical reason for these models which are old to be performing good is that components which have been used in earlier days, and now people are relaxing in these in the choice of the components what they're going to use for making the solar module. So it's very important and very much necessary for any module manufacturer to look into the components what they are going to select. So how can a module a reliable module be made? How can you guarantee the performance of the solar module for 25 years and a product warranty for 10 years? So this involves a rigorous design and development process which is going at the starting stage itself. Then judicious component selection, very much controlled manufacturing, that is not only the from the automation point of view, the environment within which we make these modules, frequent trainings and the process controls and all those stuff. Then apart from that, accelerated environmental testing to simulate the conditions of 25 years in lesser duration, because it's very difficult for us to, it's impossible, it's not difficult, it is impossible for any module manufacturers to wait for 25 years to decide whether I should go with this component or not. To avoid that, there are climatic chambers in which we can change the temperature, humidity levels, and we can compress these 25 years across in few months. So by doing this, we can determine whether a component is good or bad. For which there are typical standards across typical standards set by laboratories like like Underwriter Laboratories or International Electrotechnical Commission, that is IEC. So within which we can determine whether the components what we are going to use are good or bad. And above all, the major thing which is required is the commitment and mechanisms for quick response to the commitment that we are going to use proper components or suitable components for the desired lifetime. Then quick response, that is anything which is observed to be not in line with the requirements, need to be addressed as soon as possible. Now, few of the investments what Renesas made in terms of the module manufacturing lines, if you see, all the lines, all the machines are from the European regions, either Germany, Italy or so. So the Tauber Stingers what we have in Renesas are Team Technic. The laminators what we have are Meyer Burger, which are 3-stage laminators. We have EL imaging, which is like an X-ray for a solar module to understand where the cell crack is there also, and which would help us to say, okay, this module is having a cell crack, so put it across, means downgrade the module and not to ship the module to the customer. We have this EL imaging at 2 locations, that is pre-lamination and post-lamination. Then RTV curing chamber, so that RTV cures within the specified duration uniformly across the solar modules. We have a Spire Sun simulator, which would test the modules, and then the complete lines are automated so that there won't be any manual movement, which would typically cause, which might typically cause cracks in a solar cells and so on. So, how are we saying that our products are warranted for 25 years or plus? Is judicial material selections. Our product excellence centers for design and development, what we have at our facilities, state-of-the-art manufacturing equipments, what we have opted for manufacturing these products, and then certifications and extended reliability program, certifications from third-party agencies and extended reliability program, which we continuously do across our across our manufacturing lines by selecting random samples, which are far more than the prescribed standards. So our quality assurance is supported by technology excellence. So we are going to look into few failures what we have seen, how Renesas is going to address, how Renesas is trying to address those issues. So one of the first thing what we would like to show you is discolorized or delamination of the encapsulant. So this could be caused by poor encapsulant, that is poor quality of the encapsulant, that is ethyl vinyl acetate EVA in this case, or poor lamination process. So in how Renewsys can assure that we are going to solve this problem is Renewsys uses its own encapsulant material. It is not going to use any other vendor's encapsulant. We have a factory in Bangalore where we do manufacture our encapsulant. Though it is an internal source where we buy encapsulant from, but still it will undergo quality checks at our module manufacturing in similar way to others. Then apart from that, in terms of lamination, okay, since we have a 3-stage Meyer-Burger laminators, which is having both electrical as well as oil heating for uniform lamination across the size of the module or the lamination bed, we will have a consistent lamination. We are going to go for weekly checks of gel strengths, peel strengths, uniformity checks across the laminator in terms of temperature and vacuum checks. So these are going to promise us that we are going to give a module which is not going to be affected by discoloration or delamination of the module. And randomly picked up samples from these production lines are being tested in our product excellence centers for much more durations than what it is there in the standards to see any failures. Now coming to the other defect, like this is a hotspot. Hotspot basically is the major reason for hotspot creation is either any which way. If you are going to reduce the amount of current flow across the complete module because of a one cell, it is going to create a hotspot. It can be due to shade, it can be due to improper soldering bonds, or cells having micro cracks which are going to detach certain piece of a solar cell from the circuit, reverse current flow, and so on, or even defective bypass diodes. So since we are using a Team Technique Tabor and Stingers, which are infrared, which is a non-contact soldering process. So the amount of micro cracks it's going to create, or the strength of soldering which is desired to be created has been created. So there is no issue in terms of soldering and micro cracks. Now coming to other scope of micro cracks is the lamination process, where certain amount of pressure is applied onto the solar module to laminate these encapsulants. We have a 3-stage laminators which are operating at lower pressures. So the amount of stress which is being passed on to the solar cell during lamination process is less. And at the same time, we have yield inspections, 100% yield inspection across the manufacturing, which would help us to detect whether we are having such issues or not. Then these diode failures, the people who work and who install the junction boxes onto the module are going to have ESD protection. So any electrostatic which is developed is not passed on to the junction box. Unlike others, it is being discharged to the ESD stations. Coming to snail trails or micro cracks, typically if you see a solar module in the initial days, you might not find it out. But once the modules are installed in the field, due to the moisture ingress from the backsheet side, which would be happening, the moisture ingress is going to pass on through EVA to the solar cell, and through the cracks or the micro cracks, it's going to corrode the silver on the front side, which is going to appear in a random pattern, which typically is like a snail, the trail left by a snail when it is passing on. So these are one of the few reasons for this are the micro cracks which are generated and which are allowed to pass through the manufacturing lines, and some inherent cell defects. So the amount of micro cracks what you generate typically depends upon your manual manufacturing process. So the more automated it is, the less chance that you are going to move the module manually, and less chance that you are going to have micro cracks. And since since solar cells need to be connected in series, we need to heat them. And when we are going to heat which is called a soldering procedure, the soldering procedure, since we are in Tavern in Team Technique, it is done by infrared, which is non-contact. The amount of stress it's going to pass on to the solar cells is less, and 100% inspection of the solar cells and EL imaging of pre and post laminations are going to help us understand how many modules, or if at all any module is having, to pass it on to a lower grade, not to be sold to the customers. Apart from this, we randomly select samples across the production floor in order to identify these defects, and we send it across thermal cycling process, and we are going to generally thermal cycling requirement is around 200 cycles, whereas we extend it up to 600 cycles to see its performance. Interconnect breakage failures. This is one of failures which could lead to hotspot as well. Okay, that is basically due to the improper soldering procedure. Inconsistent solder material being stuck at one place, misaligned solar cells, which would break the interconnecting copper which is being used for connecting the solar cells. So the placements of the solar cells in the Tavern Stinger machine, that is in TT, is very, very accurate, which in our case is going to address this issue. Apart from this, we are stringent quality criteria, strictly adhering to the standards requirements in terms of clearance and creepage distances will also help us to avoid this problem. Then, in order to understand, we also do tap pull tests across the shifts across the day multiple times to understand how uniform our soldering quality is and so on. Now coming to this backsheet cracking or discoloration, this will result in power loss, and this will also result in degradation of the solar cells, not only in terms of power, in terms of the product reliability as well. So what are the reasons typically for this is a coated backsheet. So how are we addressing this issue? We are manufacturing our own backsheets in Bangalore along with the EVA, and we are going to use our own backsheets. That is the first point. Second, we are always using 3-layered backsheets. We are not going to use 2-layered coated backsheets. The quality of the raw materials, not only at the backsheet manufacturing plant, which they are going to inspect, which we are going to get it from our vendors, but at our module manufacturing plant also, though the backsheet is in-house, it is still treated as an external source, and all the quality procedures or quality checks at the incoming are being done. So we are having higher interlayer radiation of greater than 5 Newton per centimeter and high moisture barrier of 1.6 gram. And other proactive measures what we follow are pressure cooker test at the raw material stage to see its hydrolytic addition. Then from the module point of view, we have a program called reliability monitoring program, wherein which randomly selected samples across the manufacturing lines will undergo complete IEC UL standard testings and beyond. Now coming to this, which is potential induced degradation. This is typically caused by higher potentials in which modules are installed in the field, associated by the heat and the humidity in those conditions. In order this to occur, we need to have a damp surface and a higher potential at which it operates. So one of the major reasons what we have understood for PID to occur is cells, the solar cells does not have enough protection, that is enough electric strength to withstand the high potential barriers, means high potentials in the installed systems. Then EVA grade not being PID resistant, that is again the dielectric strength of EVA is not high enough to protect these modules from PID effect. Okay, so how do we address this? Renesas does make PID cells. We have an additional step where in which solar cells are deposited with oxide layer to protect solar cell from this potential induced degradation. Apart from that, all the solar cells, any other solar cell which we are going to procure from outside, at IQC stage itself, will undergo PID testing in using in-house product excellence centers and determine whether it is a PID free cell or not. Any non-PID cell is not used for production. And the EVA what we are using is again PID resistance. The dosage is done for the PID production where the dielectric stands for a normal EVA around 10 power 14, whereas in this case it is around 10 power 15 to 16. How we ensure is we are using yield imaging in the product excellence centers as well to determine whether any of the cells in a module after PID test are darkening or not, or any effect is there or not. Then the other thing what we are doing is a reliability monitoring program, which has PID incorporated. Though the standard does not have a PID, but we have included PID. And in this case, PID generally it is done for 96 hours, but whereas in our case we extend it to 288 hours at 85% humidity and 85 degrees centigrade. So this is our typical reliability monitoring program scheme. The ones which are in orange or the top ones which are of different colors show that these are the standard requirements of either IEC or UL, that is International Electrotechnical Commission, or unrelated laboratories recommended specifications of the duration of testing and conditions. But in our case, what we do is whatever the models we select in RMP program, or whenever a new material is or a new BOM component is being added, we are going to do this, but we are not going to stop at those, but we are going to extend. If we consider hotspot, we are going to do it for 12 weeks. If we consider the sequence test, the humidity freeze is extended up to 50 cycles. And similarly, thermal cycling, though the prescribed is 200 cycles, we go up to 600 cycles. Similarly, for damp it, it is 1000 hours which is required from the standard, but we go up to 3000 hours, and PID is 96 hours which is required, but we do for 288 hours. So with this, I'd like to end my presentation. Any questions are welcome, please.
Hello everyone. So start asking questions.
Hello, Sandeep sir. I listen.
Yes.
Yeah, sir. My question is how to prevent micro crack during transportation and installation. This is a major issue.
Yes, I agree. That is a major issue. Transport, actually, see, if you look into the new packing schemes, whichever are coming up, right, in order to avoid these cracks which are generated during transport, the modules are now being bundled together. Whereas in earlier cases, we used to have a box in which modules are individual to each other and they can flap. Okay, now modules are bundled together so that there won't be any movement when you are doing transportations. Instead of a single module flapping, it will means like 20-25 modules are beyond are being packed together. So it becomes a block. That is how it is addressed in terms of transportation. Now coming to installation point of view, so it depends upon the skill level and the equipment what we are going to use. So that depends upon the person who is going to install. So we can't do anything from that point of view, because if someone is careful.
Yeah, I have seen many times in LinkedIn people are working on module during installation. So in case future 2 or 3 after 2 or 3 years, he will complain to manufacturer like us.
Yeah.
That's why I'm addressing this. Is there any opportunity to reduce this type of micro crack via cell thickness or other process?
See, on the other side, actually, cell thickness. If you see, if you had seen my presentation on the stat, actually, if you see the driver for the product development and all those stuff is lowering the installation cost and lowering the LCOE rate. So there is option of increasing the wafer thickness. It's on the other side, it's going to go down and it's going to go to 150, 160 microns. Okay, so it is up to us, whoever are installing, to be more careful. And actually, from module manufacturing point of view, actually, it's our responsibility to educate them that you have to be careful. These are the things that you have to take care when you are going to install a solar module upfront itself.
Yeah. My second question is right now that we are saying that the cell thickness are day by day decreasing.
Yes.
So in 2030 we are using 230 to 40 micron, but now at a 180 micron. Nowadays there is a number of bus bar going to increase and cell bus bar area is little bit decreasing, and in the same ratio ribbon thickness is also increasing. There is a chances of micro crack.
Okay. See, actually, the major reason for decreasing wafer size, one of the major reason is the doping. Okay. The earlier wafers are boron doped. Okay. Now they are gallium doped. Okay. It is going to increase the cost, so they are cutting down on the cost on that. Now, in terms of cracks, whatever you are saying, micro cracks. Okay. When you going to use a round wire, okay, typically you have to increase the EVA thickness. Not going to be the same EVA thickness what industry has been following since past 10-15 years, like which is typically around 450 microns. No, it is not going to happen. So we have to increase it to maybe around 600-650 microns with a higher GSM. Okay, that is the only solution we have.
Okay, thank you, sir. Thank you for such a good information. I appreciate it.
Thanks.
Okay, so next question from Mr. Hassan Nazir.
Yes, sir. I have addressed this question.
Okay, so now next from Mr. Costeto.
Let me ask you something. When you show us 25 years plus, what it means? This solar panel can work 40 years? How long the maximum you believe we can offer to our client, or a solar farm can work with this kind of solar panels? What it means 25 plus years? Thank you.
Depending upon the technology what you are going to choose, depending upon the installation site what you are going to choose, depending upon how you are going to maintain your plant when you install. And just now we have discussed from other question from Mr. Hassan also that the care what you take during installation, all these are going to determine together whether it is 10 years, 25 years, or 30 years, or 40 years. So yes, solar modules can work much beyond 25. It can go up to 30. It can go up to 40. Definitely 30 is definitely possible with the current technologies.
Okay. When we install, we do the delivery, the transportation, the carrier is all good, and we do the OEM of the solar farm every single day, every single week and year. Do you believe, example, this next solar panel you are offering us next year, 510 watts, it will working, example, direct? 30 years, we can offer 30 years guarantee to our clients?
In terms of performance, yes. Provided it is being maintained appropriately. That is the key component what we have to observe. It looks like we are maintaining the plant properly, but practically, if you look into the maintaining the plant does not mean only looking to the connections or cleaning the panel and all those stuff, but doing the health check as well. That is looking into the EL images, thermal imaging frequently to determine whether we have any cracks developed in the solar cells and solar modules.
Great. Thank you so much.
Yeah. Thank you.
Thank you, Rogerio. So, is there anyone who wants to ask the question? Okay, so Monica,
Yes.
go ahead.
Thank you. More than a question, I just want to say a message in Spanish. Para la gente que habla español, si quieren que les traduzca alguna pregunta, con gusto les podemos ayudar. I just want to say that I can translate any question that they have. Thank you.
Sí, Moni, sí, yo acá con Raúl Félix Sime. Moni, mira, es interesante el webinar. Sin embargo, concretamente lo que veo es, he leído un poquito de la marca de ustedes, de los productos de ustedes, y lo que me gustaría es tener un catálogo, cuáles son los productos que tienen, las capacidades que tienen. Ahorita vi algunas, los rendimientos, ya los vi ahorita más o menos, ya me queda claro el producto, pero lo que sí me gustaría a nosotros es tener un catálogo, los tiempos de entrega y por supuesto con eso ya estaríamos nosotros solicitando cotizaciones y de esta manera integrarlos a nuestro mercado.
Claro que sí, Raúl. Muchas gracias. Just to translate Harsh, Raúl would like to receive all our technical information, catalog, pricing, delivery times, etc. So we can address that after the conversation and we will make it happen. Raúl, te vamos a mandar toda esta información. En cuanto acabe la presentación, yo me pongo en contacto contigo.
Muchas gracias y la verdad que no puedo hablar inglés porque es muy raquítico.
No te preocupes, gracias por acompañarnos.
Gracias.
Thank you, Harsh. That's it for me.
Noted, Monica. I will share all the details.
Thank you.
Okay, any more questions?